Okay, lovely. Is my screen visible to all of you?
Yes, it is.
Yes,
Yes,
sir.
sir.
Lovely. Okay, so this is a small presentation on. It's actually a first presentation. First time we're going to talk about this new topic. It's quite exciting because this is the first time we're trying this approach of teaching you guys things other than your boring. Well, let's not call it boring, but we all know what it is. But the syllabus that you guys have been dealing with, there is a whole world other than that also, right? This is not syllabus is not all it is. Here all our hopes is to jump into delve into a new kind of a subject. Maybe all of us will come out of it with some new ideas and with some new convictions, and maybe get motivated in life about these very fundamental and very beautiful questions that all of us have been wondering since a long time. And that is where we start. Humans have been looking up since their dawn. Come, let's carry on that tradition, that age old tradition. Questions are obviously recommended. So, anytime you guys have a question, just speak up. This It's just us. We already know each other. We've already taken your classes, so we're pretty chill together. This presentation,
Sir.
yes, go ahead, Yash. Or was it Hasper? You were saying something?
This we recorded, sir.
I'm sorry?
Sir, I was asking if this would be recorded.
Yes, this is being recorded.
Yeah, sir.
Lovely, lovely. Okay, so this particular presentation, this first presentation, there are three fundamental questions that I want to answer about stargazing, about looking up in general. The question of where, the question of when, and the question of what. Starting with this theme, first thing what we're going to talk about is what is called the birth of a star. Stars, as we look up in the night sky, we see them all around us. They're formed in these immense clouds of hydrogen and helium and dust called nebulas. Over the course of thousands of years, gravity causes pockets of dense matter inside the nebula to collapse under its own weight. This process is further accelerated when another star, which one is seeing right here, what you see here is what we call a neutron star. A star which has already exploded all matter, the normal kind of matter, the electrons and the protons are out of the system, and what is left are just neutrons. So all the protons and the electrons which were left also, they have combined together to form neutrons, and what is left is just a neutron. But this is happening after an explosion, after a supernova event happening. This supernova event that would have happened in the past would have caused shock waves to go through the nebula, causing these contraction and expansion events to happen. So already a system is very hot, and then you send these shock waves through the system, causing additional contraction. So what does that cause? It causes it to begin to turn upon itself and heat up, forming what are called embryoic stars or a protostar, an initial form of a star. Here is an example of one. Lovely. Getting started with stargazing. Keep looking up. Let's answer the first question, which is the where question. Living in cities has many problems, and especially for amateur astronomers, I hope to be one of them. It is worse because not only do buildings all around us restrict the viewing area, individual light sources from houses combine together and light up the city night sky, just like the sun does during the day, hiding the heavens from us. You want as much of a view of the sky as possible. So what do you need to do? is go.
Sir,
Yes, can you hear me?
yes, sir, I can hear you. Sir, are you presenting slide one?
No.
सर स्लाइड वन दिख रही है वही पहले लुकिंग अप प्रेजेंटर वाली.
Give me a second. What can you see now?
Yes sir, अब
Can
आए slide 6.
uh, you weren't able to see the previous slides?
Yes sir.
No, sir.
ये
Sir,
सारी slides नहीं देखी आपने?
no no
No,
no.
sir.
Hey, that is weird. ये zoom क्यों कर रहा है सारी चीजें?
That is
Okay.
why I wondered when you but वहाँ पे कुछ नहीं था.
Ah, okay. Okay. Let's go through it again. No worries, no worries. So here, what essentially you're seeing is a nebula. This is an immensely hot gas, a collection of gas. When I say gas in the universe, I mostly talk about hydrogen and helium because that's the majority of all the gases that are there. And additional dust is also present throughout the universe. These nebulas have both hydrogen, helium, and a lot of dust. Over the course of thousands of years, as I said, gravity causes these pockets of dense matter inside the nebula to collapse under their own weight. Here, what you can see, if you can see it on the slide, is what is called a neutron star. So this is essentially how it looks like. Uh, the process of star formation is further accelerated by such events. Events which I talk about are supernova, which is essentially the death of a star, which we will come to by the end of this talk. But these kinds of supernova events, when they happen near the nebula, they cause shock waves across, and you can see the shock waves, what kind of density formations these shock waves are forming in the background. If you can see here in the background, these are the density waves that are essentially forming here. And this is what it ends up like. It just ends up becoming multiple star. This is how it was initially, and all the gas just goes away, and what remains is an embryoic star, or what is called a protostar. So now, keep getting started. Can you hear me?
Yes, sir.
Yes sir.
The
Yes
question.
sir.
Lovely. Why is my video off?
Sir, sir.
This is super weird. Okay. Um, Sorry, apologies. Technical issues. Okay, so getting started with stargazing. Keep looking up. Getting up high. First of all, we are answering the question of where. Living in cities, as I said, has many problems, especially for amateur astronomers. It is worse because not only do buildings all around us restrict our viewing area, individual light sources from houses combine together and light up the city night sky, just like the sun does during the day, hiding the heavens from us. So what you want to do is to go as high or as away from any kind of light pollution as possible. Since most of the objects in the night sky are not very bright, what you want is you want to adapt your eyes to the dark. So, meaning that you want to be as far away from street lights as possible. Because one street light can knock out your dark adaptation for about 20 minutes. So if you just come across a street light while doing some night sky observation, 20 minutes of your night sky absolutely gone. You won't be able to see objects that you would have been able to see if your eyes were adapted to the dark. So where? Get up high. Why I'm saying that? Because this is essentially the distribution of how stars are in the typical night skies. For example, in the inner city night skies, you typically are able to see just around 5 to 10 stars. In cities, for example, here in Delhi, where I am right now, we would be able to see about 50 stars, 50 to maybe 80 stars on a very lucky day with no clouds at all, but not a lot more than that. You need to go to the suburban areas around Delhi, for example. If you go to outskirts of Noida or Gurgaon, you'll be able to see is around 100 to 120 stars. You'll need to go to rural areas in order to actually see the night sky, actually see the magnificent beauty that is the night sky, where you're able to see around 300 to 500 stars. But excellent night sky vision is when you're able to see the maximum amount of stars which are visible from Earth via naked eye, which is around 2,500 to 3,000. You need to go to very high altitudes and very far away places. Now, that's the where. What about the when? What you want to look for in order to time your expedition or time when you want to go out for a night sky is if you can brave the cold, the sky is its best on crisp, clear winter nights when there is no humidity in the air. So what you want is cold, dry, dark nights. Summer evenings tend to produce haze. That is why you want. That is why you want winter nights, because haze is essentially hot air, pockets of air which essentially move up. And since there is this density fluctuation that is always happening because there's hot air which is always rising in summers, your view will always be blurred. So look for cold, dark, and dark nights. Then look for the moon, because the moon, from what I feel, is sometimes the most overlooked objects in the night sky, because it's great. It's great for city dwellers, for people like me who cannot see a lot of stars. The moon is always present. Uh, so here in this slide, you can see the different phases of the moon. The sunlight is coming from the right. The new moon is essentially when there is no moon at all. The moon is just being born at that point in time. This happens when all the light is falling on the moon on the other side. Since you already know that the moon is tidally locked with the earth, so only one face of the moon is always facing us. So you're only able to see one face of the moon always. So when the opposite side of the moon is lit, the side which you can see is absolutely dark, and hence what you're seeing is a new moon or no moon at all. Then as time goes on, as days go on, what you start seeing are crescents, small crescents which start appearing. Since the moon is growing, we are calling it the waxing crescent, because when you're waxing things, it essentially becomes thicker. That's the main thought behind it. Then it goes on to form its first quadrant when you are able to see the half moon. Then it waxes further, making the waxing gibbous phase. Gibbous is essentially the bigger form of the moon, the smaller form of the moon being called crescent, and the bigger form of the moon being called gibbous. So there is waxing crescent, so increasing crescent, and waxing gibbous or increasing gibbous. And there are also waning gibbous, which is decreasing big moon, or waning crescent or decreasing crescent moon. So that's essentially how we talk about the moon. We have this kind of a nomenclature for the moon. Now, what do you want to look for apart from the moon? Well, everything you want to know, you need to know, is available in what is called a star chart. Just like an atlas for countries, a star chart is the best way to learn the skies. You don't necessarily need those anymore, since you can download them over the internet and you have modern technology. But I still love them, and because I still recommend them because they're awesome and they give you a lot of information. Here is an example of an evening sky map. This is last month's March 2021. Here you can see all the patterns or all the night sky objects that you can see in the sky that particular month. In this case, the month of March in the northern hemisphere. You can also see the different objects and descriptions of different objects and the times at which you'll be able to see these objects in the night sky. There is some additional information about the celestial objects that you can see, some tips for observing the night sky, some astronomical glossaries, so some definitions of objects and some. Um, then there's also divisions of easily seen objects with binoculars, and easily seen objects with telescopes. So a lot of information is present in these star charts. A lot of very useful information, I would say, is present in these star charts. Now, moving on, there's obviously a lot of new technology that has come in. There are some good new apps. Some I would recommend if you want to continue with this series of lectures, especially for you to download them so that it just becomes more involved, so that you can also do the simulations at your end. You can also see what we are seeing in class at your end just by doing it yourself. And exploring things is always amazing. The first software that I want to talk about is Stellarium. This is an amazing software. It's a standard software on Linux operating systems. It's excellent. It lets you see the position of planets, stars, and whatever you want to see in the night sky. We'll see one video from this particular software later on in this slide. Then there is Starwalk 2. This is mobile based or Star Tracker. Both of them are available on both the Google Play Store and the Apple App Store. Then you have Google Sky Map or Exoplanet, which is essentially Google's version of Star Tracker. So it's essentially based on Google Maps. So it's like Google Maps for the sky. They have an interesting thing going on there. You can have a look at that also. And there's also an Apple version of exactly this, and it's called Exoplanet. The Apple version is called Exoplanet. Yes. You can download the monthly star charts as well. So the star charts you see here. This has been downloaded from this link down here, www.skymaps.com/downloads.html. Now, moving on, let's learn something new. All of this that I've been talking about is might be slightly known, but let's learn about differentiating between planets and stars. Now you're looking up. Now you're seeing objects in the night sky. But what are you seeing? Is the thing that you're seeing a planet or a star? The most fundamental difference. First of all, if the bright light in the night sky sparkles, it's a star. A very well known fact. We've all heard the nursery rhyme "Twinkle Twinkle Little Star." Exactly comes from that. If the object that you're seeing does not sparkle and it appears stationary, it's most probably a planet. It is always a planet. And if an object is much brighter than those around it, there's a good chance that it's going to be a planet. Why is that? That's because planets are objects which are way closer to us with respect to the stars that we see in the night sky, and hence they're way brighter because luminosity goes down as 1 by r squared. Here, what you're seeing right now is a time lapse. As I said, we're going to talk about time lapses. Um, we're going to talk about time lapses, and the software that I'm using here is Stellarium. So the point I want to make here is ancient travelers and modern sailors, pilots as well, use stars to make their voyages through lands and to discover new lands. A quick look at the time lapse photography will show that the stars are not static in our night skies, but instead they streak across the sky from east to west as the earth revolves. There are many ways of locating directions. If you ever become Voyager, if you ever get stuck in forest, it's always a good idea to know what direction you're looking at. There are some standard stars that people talk about. For example, Polaris in the northern hemisphere, which is at the tail of Ursa Minor. We will talk about these particular stars and how to essentially just look at the night sky and figure out directions. We will talk about that in a future slide. Here, let's talk about a very simple experiment that you yourself can do at home and to figure out the direction that you're looking at, whether it's east, west, north, or south. What is the small experiment? Well, take two sticks, small sticks, and plant them on the ground about a yard apart from each other. Now, pick a star, a bright star in the night sky, and adjust yourself such that you're behind both of these sticks, and these sticks are aligned with the star in front of you. It obviously helps if the star is bright for easily keep track of it. Now, wait for the star to move. As soon as the star moves out of alignment from the two sticks, if the star went left, you know the direction you're facing is north. If the star went right, you know the direction you're facing is south. If the star went up, it's east. And if the star went down, it's west. But not only that, if the star goes, but not only that, you can talk about in directions in between these directions as well. So, for example, if the star goes left and up, then you know you're looking towards northeast. If the star goes left and down, you know you're looking towards northwest. If the star goes right and up, you know you're looking towards southeast. And if the star goes right and down, you know you're looking towards southwest. So this is a very simple technique, a very simple way of figuring out what direction you're looking at. You don't have to know about what stars are there at night. It's obviously good, but these are small tricks, small experiments you can do at home, just to figure things out, just to figure out the world around you slightly better. Now, moving on, let's look for the International Space Station. Why? Because it's the biggest man-made object in space. And watching the largest man-made object in the sky is an amazing experience. This is a home for the crews of astronauts and cosmonauts living in space at this moment in time. The space station also has a unique science laboratory. Several nations work together to build and use the space station. The space station was not, it's a humongous object, and it wasn't assembled down on Earth. Parts of it were taken up, and it was actually assembled in space by astronauts. The space station orbits the Earth at an average altitude of approximately 400 kilometers and an average speed of 7.82 kilometers per second. That means that the International Space Station orbits the entire Earth in less than 90 minutes. So every 90 minutes, you've crossed the Earth again and again and again. Sometimes what you can have is you can have the International Space Station right above your head. How do you track that? Well, NASA has made it very easy for us. NASA has a dedicated website for tracking the ISS, which is essentially spotthestation.nasa.gov. And you can also so on this website, spotthestation.nasa.gov, you can sign up, and it will actually send you alerts whenever the space station is above you. So it will ask for your location, and whenever it's above you, it will send you an alert so that you can just go out and look it up. Or if you don't want that, if you just want to see where it is in real time, you can go to www.isstracker.com, where you can track it in real time. Lovely. And lastly, use your imagination, use your eyes. People try, especially when people enter night sky observations and stargazing and looking at the stars, there's a tendency of collecting new telescopes, new binoculars, new tools. It's always a good thing to have more tools. They're not saying that, but it's also always a good thing to just sit back and use your eyes and use your imagination, just like our ancestors did thousands and thousands of years ago, for thousands and thousands of years. So try to spot characters in the sky. Orion the Hunter is a good example. Scorpion is a good example. Sirius is a star which you can see. It's quite a bright star which you can see. And with enough practice, eventually you'll know the characters in the sky by heart. And finally, as I promised, the death of a star. Here I simulated kind of a death scene of a star. So what you have is a massive star, a neutron, not a neutron star, but a massive star, and a small star, a star like the sun, just coming towards it. And as soon as the mass combines, it blows up. It just blows up. Why does it blow up? Because it's crossing the threshold mass that it needs to go supernova. So as soon as these two masses combine again in this video, you see this beautiful event, this beautiful, humongous event happen in front of you. And at the end, what is left, as you can see here, is the final left neutron star. The similar neutron star as we saw in the beginning of this lecture. Here you can see the neutron star just hanging out in space all alone after the supernova has disappeared. And that's
Sir,
it for today. Yes, go ahead.
sir, the
Go
bulk
ahead.
with which the star clashed with was also a star, right?
I'm sorry? Yes, yes, both of them were stars.
So what happened to the next one? It did
Both
not
of
go.
them just combined and just blew off.
Mean both of them blew off, right?
Yes, yes, yes.
Okay, okay, sir.
So they just combined. Here you can see them combine and just go off in the distance. Lovely. So questions, please.
Sir, why is it called a neutron star? Some specific reason for
It's
that?
yes, because it's made of neutrons. It's only made of neutrons. It is so massive. It is so massive that that in event. So we'll talk about when you're talking about modern physics, we'll talk about alpha decay, beta decay, and gamma decay, right? There's another kind of decay that there's out there, which is called an electron capture. What essentially happens is that an electron, if the energy, if the attraction gravity is so high that the electron essentially gets so close to the nucleus, gets so close to the proton that essentially the proton captures the electron and gives out a neutron. So all the protons and neutrons, most of them, first of all, they went out because of this blast, and the ones that remain get converted into neutrons. So all that remains are just neutrons. So for a long, long time, up till until the 19, I think it was 1997 when first time we detected a neutron star. But before that, it was just hypothesized that these objects would exist out there in space. And then we went out, we checked for them, and indeed we did find them. Okay, more questions, please.
And
Sir,
sir,
not a
what was
question on
that?
it.
You go first.
Go ahead,
Yeah,
answer.
fine. Sir, yeah, I had a request, sir. Please ये PPT भेज दीजिएगा.
Okie dokie.
Sir, I was asking that.
You were asking, sorry?
I was asking what threshold mass was.
Okay. So So this essentially was given by an Indian physicist, goes by the name Chandrasekhar. He won. I think he was the second Indian born to win the Nobel Prize, from what I remember. First being C. Raman. So what essentially his discovery was, and there's an interesting story of how essentially he made the discovery. Also, he said he boarded this ship to from India to London in order to go for his studies. And during this trip, he said just thinking about stars and just thinking about what happens when if you keep on adding mass, if you keep on adding mass, and then he started thinking about exactly this process of electron capture, and which was very recently discovered. I think it was discovered like 2-3 months before that, and he just read a paper on that, and that essentially triggered his imagination. What his calculations showed was that there is a mass limit which is around 2.3 to 2.5 times the mass of the sun. So every time you will hear about masses in astronomical terms, you'll always hear it with respect to the mass of the sun. So what essentially happens is that if your cluster, if your sun, or if your star, your cluster of gas has mass which is around 2.5 mass of the sun, the gravity is so strong that the electric repulsion that should essentially so many electrons, so many protons being trying to compress together, essentially overcomes the electron and proton repulsion, and hence forms this whole neutron star. So it was essentially the limit that I was talking about was exactly this mass limit. So in the simulation that I had made, I'd made the bigger star very close to 2.5 times the mass of the sun, and just had a sun which essentially just launches inside that, and I knew it was going to blow up. So that's essentially how I did that also.
Sir, if the mass difference was only 2.5 times, why was the size so large?
Mass actually does not have anything to do with the size. Actually, it does, but not technically. What has to do with the size of a star is the age of the star. So, if it's a young star, it has a lot of hydrogen, right? What does that mean? It means that there's a lot of nuclear reactions that can happen, a lot of thermodynamics that can happen, a lot of energy that can be released. So no matter how much the mass will be, the star will essentially be of a size which essentially balances the gravitational force and the thermal repulsive force. Now, once the hydrogen starts dying off, once the hydrogen starts getting exhausted, finishes off, it's still being attracted, right? So what starts happening is that higher elements, heavier elements, helium starts combining and becoming lithium, and lithium starts combining and becoming boron, carbon, nitrogen, and all these other elements are also formed. But if you go back to your in 12th class modern physics, and if you calculate the exactly mass deficit that are there, this term mass deficit that they use for essentially the mass after the reaction, before the reaction, and you just subtract the two. It's a fancy way of just saying what is the energy that is left. E is equal to m square, mass and energy is exactly the same thing. So what essentially is happening is that as higher and higher elements are being combined, more and more energy is being released. So the energy that is released when one hydrogen combine is actually very small compared to when an oxygen and oxygen combine to form element 32 or whatever. So since a lot more energy, a burst of energy start coming out, so what essentially happens is that old stars expand. They expand, they expand. That is essentially what will happen with the sun as well. The sun is going to expand and expand, and it will become a red giant. So it has to do with the age rather than the mass, because it's essentially about how much gas, how much hydrogen is there, how much helium is there, and how many other things are there. Does that answer your question?
Yes, sir.
Lovely. Any other question?
So you said that the sky needs to be dry. Why?
Yes.
Why is it?
Because if it's humid, think about it yourself. If it's humid, it's your visibility is low, right? It's always low, and especially when it's cold and humid. Because when it's cold and humid, what do you have? You have fog,
Yes,
right?
sir.
Makes sense.
Yes, sir.
Lovely.
Sir,
Yes, go ahead.
how are nebulas formed?
Nebulas are nebula. See, for that we'll talk about exactly this question in later topics. But let me give you a small answer about for this. So what essentially happens in every galaxy there are a lot of, obviously, what is the galaxy made of? It's made of dust and hydrogen and helium, right? So there are these giant clusters of gases. So, for example, if you look up in the night sky, you know how the Orion Nebula. How does Orion look like?
No, sir.
Lovely. I will show you how Orion looks like then. Let me let me open Stellaring for you. So essentially, what I want to show is that you have been looking at nebulas all your life, and you've never really noticed it. Uh, because they essentially look like stars, but since they're so far away. But but if you have a good enough telescope, you're able to delve inside. So let's increase the time here.
There's a patch on the screen.
There's a patch on the screen. Yes, is the patch gone?
Yes, sir.
Lovely. Yeah, I'm pressing the wrong button. Shit. Okay, wait. Just constellation. First, I'll show you the constellation, and then I'll show you the Orion. So, so there's this pattern that essentially forms where you have these three stars that are in a line. These three stars are very common in the night sky. Have you ever noticed these three stars together? Especially in the northern hemisphere, you see this all the time. It's like this here, three stars that will be in a line. Have you seen this?
Probably, sir.
Probably, yes. So here, actually, the middle one is not really a star. It's actually what is called the Orion Nebula. So it's essentially something like this. So nebulas are essentially just clusters of gases, and gases are obviously present everywhere because matter is present of everywhere. So whenever a major chunk of this gas gets collected, which gets collected everywhere, it forms this nebula. Or what starts happening is that there are these there are these sites, there are these dots that you can see here, right? For example, this bright here, this bright here, this bright here. What is happening here is that there is accumulation of matter that is happening, and stars are essentially forming here. So these gas clouds are everywhere. They are literally everywhere in the galaxy, and hence in the universe, because there are a lot of galaxies in the universe as well. Does that answer your question?
Yes, sir.
Lovely.
Sir,
Go ahead.
so I had another question that, sir, there was a star called the North Star.
Yes, Polaris.
So, sir, you just said that stars change positions through the night. So, how
Yes.
could it be at the
Yes,
same
lovely,
position?
lovely question, lovely question. So, yes, so you saw the stars go round, right?
Yes, sir.
Polaris is in a very very special position. Uh, just give me a second. I'm googling. Yes. Polaris is in a very very special position, and it's just by happenstance. It's not like there is some reason behind what behind it being exactly at that point in the sky. But as you can see here, uh, Polaris is what is this video? Sorry, not a video. Yes, Polaris is actually right in the center of the rotational axis. So it's just by happenstance that, so see, the Earth is rotating, right? If you have a star which is exactly on the axis, in such that if you're standing on the North Pole, if you're literally standing on the North Pole, if you look up at the zenith, what will you see? You will see Polaris. You will see Northern Star. So it is essentially along the axis of your rotation. So whenever something is along the axis of your rotation, it will stay stationary because things will rotate around it, right? Actually, if you actually go ahead and see Polaris, it actually does rotate. But it rotates very very slightly. It rotates. If you see under, for example, in this fourth photo, in this third photo here, the inside one also has a very very small circle. So Polaris does move, but it moves only slightly. Does that answer your question?
Yes, sir. So, but during the revolution of the Earth, sir,
Hmm.
that time also Polaris does not change its position.
Yeah. Polaris. You yes, only 6 months you will be able to see it, right? Only half of the year you'll be able to see it, because for the rest half of the year it's below the horizon, right? Earth is tilted, and you're on this side, and then you're on this side. So half of the time of the year you're seeing this part, then you're seeing the other part, right? That's essentially why. Make sense?
Yes, sir.
Lovely. Anything else?
No, sir.
Lovely. I hope this was helpful,
I'm done.
and we will continue to have something like this on basis of this. I have a whole plan in my head of how I'm going to progress with this. I have set up a whole syllabus for all of this, such that it also complements. Not It's not just a completely out of the box thing. It So that it also somehow complements your exams and your school education, in the sense that you will find a lot of places where you have direct applications of thermodynamics, or direct applications of planetary motion or gravity, or those are obvious examples. But there are other more interesting examples as well. For example, the virial theorem has a very very interesting derivation of how you can actually estimate the temperature of the sun just by using with the virial theorem. So we will do all those interesting things as well in this course, which actually might be helpful in some of the interviews, if any one of you goes for those things. Chalo, let's stop here then, and let's see each other next week.
Thank you, sir.
Yes, sir. Thank you, sir.
Lovely, no worries.